Hello, this video is for the Argonia Cup competition. This video is for one of the teams from the University of Illinois at Chicago. Our team name is Team 2. Our team number is 2109. Now we will be going over the flight simulation portion of this video. Here you can see our rocket as shown in the open rocket program. We're doing head-in deployment. This coupler is going to be between the nose cone and the body tube is where our bay, our electronics bay, is going to go, and that is going to control the release of the parachutes and something we're calling a sabo. The sabo is going to hold a drone, and that drone is going to be used to deliver the golf ball, right? So rocket comes out. When it opens up for a parachute to come out, the sabo is also going to be released. You're going to hear more about that later, and then the sabo can release the drone, and the drone can deliver the golf ball. Right, and here we can see all of the necessary components. The main takeaways is our apogee is 8,928 feet, which is greater than the 8,000 feet required for this competition. Our motor is an L95W-P. Our thrust to weight ratio I calculated to be 6.7, which is greater than the 5. A thrust ratio of 5 is required per the rules of the competition. So we pass that requirement. Our velocity off the rail is about 60 feet per second, as shown in Open Rocket. Because we can export these flight results to a spreadsheet, and we can look in the spreadsheet to see more detailed information. I wanted to show that quickly. Right, we can export our flight simulation, and we can see various things. But what is of note? Total velocity in feet per second. We scroll down. There's the event called liftoff, but the event launch rod, when our rocket leaves the rod, is at T 0.47, 0.07. Our speed. So this is our speed. Speed off the rail, 60. A speed of 30 is generally considered safe. So through all of these metrics, our rocket is not only going to have a safe flight, it is also going to meet the rules required by this competition. Thank you.
The electronics bay for this rocket is approximately a foot long and has dual density, meaning it has one backup altimeter. Each plate is made of plywood and holds straddle altimeter, terminal block, and battery holder. Due to weight constraint, each plate was designed to be as small as possible. The plates are connected to the rods through rod holders, which are 3D printed. This electronics bay also uses 2 barrel jack switches as opposed to screw switches. Further on, the bulk plates are made of fiberglass and hold a U-bolt and terminal block. You might notice that the plates have many additional holes that are not used for anything. That is because the team decided to be more cost efficient and reuse bulk plates from another 6-inch rocket. The black powder will be stored in secured surgical tubing as opposed to copper cups that the team usually uses. The surgical tubing is much lighter than the copper cups, which again helps with the weight limit.
In order to safely deploy the drone from the rocket, we're using a sabo to contain it. This 3D printed cylindrical structure sits inside the rocket body and keeps the drone safe when it is going up in the rocket. Pictured here is what the sabo's body looks like. The sabo is deployed with the rocket's main parachute and has a parachute of its own which orients the sabo to its proper position, which allows the drone to drop out of it when it is ready to be released. Inside the sabo, there is a latching mechanism that holds the drone inside. Essentially, this is a linear actuator attached to a latch. The latch goes through a zip tie attached to the drone, and an Arduino set up with an altimeter powered by a 9-volt battery inside the sabo moves the linear actuator once it is ready to be released and reaches a certain altitude. Doing so allows the drone to fall out of the bottom of the sabo and fly off. The inner portion of the sabo will be filled with a rigid foam in order to keep the drone in place so it does not get damaged in flight.
Hi there, my name is Philip Carson. I'm the drone lead. So what we were planning to do last year is we were going to use a commercial off-the-shelf drone and use its return to home feature to try and bring the golf ball payload back to the target site. as we worked on it, some issues cropped up that we were not expecting, and it became less and less feasible to do this under launch conditions where you don't have a human interacting with the controller or something like that. So we decided to pivot this year to a custom drone platform. We're using Arduino. This just gives us a lot more options and freedoms and different routes we can use this drone platform in future competitions, whether it be Argonia Cup or anything else. The drone is going to be roughly the same size and shape as last year's drone. This is a very early prototype frame and body with some motors on it. It's the same size and shape because it's pretty much the biggest drone you can fit inside a 6-inch rocket, and we didn't want Sabo Team to have to redesign everything that they were working on from last year. The basic operation of the drone is going to be it's coming down with the Sabo. Sabo releases it. Drone's going to detect using altitude and sudden change in acceleration. It's going to detect that it's been released. It's going to start to hover around 100 feet or so. It's going to use its compass and GPS to calculate where it is, turn towards the coordinates of the target location, and just fly on over. And then once it reaches the target location, it's just going to slowly drop down, and then hopefully we'll be close enough to win. Due to some rounding with the Arduino, we expect to be plus or minus 100 feet of the target destination if everything operates normally and there are no major hiccups.